Hello, my name is Qing-Dong. I'm from Stockholm University in Sweden. My talk is from Casimir effect to quantum atmosphere. The keywords in this talk are symmetry breaking and quantum fluctuations. So in the first part of this talk, I will show you that symmetry breaking plus quantum fluctuations gives the anomalous force. We call it Casimir effect. And in the second part, I will show that symmetry breaking plus quantum fluctuations leads to anomalous spectrum. And there we introduce the concept of quantum atmosphere. So at last, I will give a brief conclusion. I would like to thank my collaborators. On the theoretical side is Frank Wilczek. And this work, this talk is an essential summary of these following works. On the experimental side, I would like to thank my collaborators in China. So we recently posted a paper, an experimental paper on demonstrating the quantum atmosphere. So let me first introduce Casimir effect. The Casimir effect says if we have two plates in the vacuum, they will attract to each other. Classically, this is impossible, but quantum fluctuation can make these two plates relate to each other, and there's a net attractive force between them. And because it's a quantum effect, the force is proportional to the h bar, and because it's a quantum electrodynamics, there should be a c there, photon velocity, and also the force should proportional to the area of the plate. And because photon is massless, the force is in a power law fashion. So if you work out the dimension, you will see that n must be equal to 4. If you want to calculate the Casimir effect between arbitrary materials and of arbitrary shapes, you need to calculate such a Feynman diagrams. This is a two photon exchange Feynman diagrams. The Vigo line represents photon propagators. You can you can relate this Feynman diagram to this following formula. So a photon scattered by per object A and propagate from A to B, and then scattered again by object B, and then propagate back to A. And the force is attractive because due to the boundary condition of the two plates, the photon modes in between is much less than the photon mode outside. So the more photon modes outside will push these two plates together. So in fact, there's a famous Snowball theorem on Casimir effect. So this theorem says that Casimir force is always attractive if there's a mirror symmetry, the parity symmetry. So to see this, we can find that the A and B scattering matrix and the propagators are related by this parity symmetry. And if you put this relation, substitute this relation into this formula, into the energy formula, you will see that the force is always attractive. But in recent years, there are a lot of activities in designing repositive Casimir effect, because people believe the attractive Casimir force is a disaster for nano machine designing in the future, because the attraction will make nano parts stick together. So the essential idea to design repositive Casimir force is to make A not equal to B. So namely, there's no parity symmetry of the object A and object B. They are different. And the example is, you can see this following reference. So a particular reference, you see that in quantum, as an example, in quantum Hall system, the repositive Casimir force is only a very small portion, very much smaller than the original Casimir force. So the Casimir force in these new systems are repositive Casimir force in this new system are much smaller than the normal Casimir force. So there's this effect is really difficult to measure. And here we propose Casimir force that if we fill the space between two objects with a Carrier material, repositive Casimir force can emerge. So here is an experiment setup. We don't change the shape or materials of A and B. They can be the same, but we insert the carrier materials in between. So carrier materials means the left-hand photon and right-hand photon have different phase velocity. And now if we want to calculate this effect, we need to calculate a new Feynman diagram. So the difference of this Feynman diagram is that the photon propagator goes from becomes a matrix because we need to take into a left-hand photon, right-hand photon separately. And if you calculate such a Feynman diagram, you see you will get this Casimir force. And you see that the repositive Casimir force is possible is because even A and B, there's a parity symmetry between them, but the propagator doesn't respect the parity symmetry anymore because it is carrier. So as an example, we put the Faraday materials in between two plates. You will see that the force can be repositive in some regions. So the first figure plots the ratio of the Casimir force with respect to the normal Casimir force, and L is the distance of two plates. You will see that you can see that this carrier Casimir force is in oscillation way, and also it's since this magnetic field can be larger than 1, so this carrier Casimir force can be even large. Is even larger than this normal Casimir force. Also, from Faraday material, it is a special carrier material. Its nature is the carrier of this material. The character of the phase velocity difference between the two left-hand photons and right-hand photons can be also tuned by applying an external magnetic field. So this carrier Casimir force can also be tuned by magnetic field. And then we will see that the carrier Casimir force have the following features. It's repositive in some regions, and is enhanced, and is non-monotonic, and also it's tunable. It has a lot of advantages. Now I come to the second part. So this is the second part I'm going to show is the symmetry breaking plus quantum fluctuations leads to anomalous spectra. So as an example, I will demonstrate. Suppose you have a chain insulator in the, you have a chain insulator. By definition, it's described by Chern-Simons terms on the surface. And now if you bring a spin close to the surface but not touching, so what will happen? You see this Chern-Simons terms is a break time Russell symmetry, break parity symmetry, but preserve PT symmetry. But there's no real magnetic field go out from these chain insulators. So the question is, will the spin feel a effective Zeeman field? Even though there's no real magnetic field. So if we can calculate a relevant Feynman diagrams described by this. So a Chern-Simons vortex is a 2-photon vortex interacts with an electron propagator. And if you calculate this interaction terms, you will see that this spin do feel a effective Zeeman field. And if we put the spin very close to the surface, say 10 nanometers, you will see that this effective Zeeman field is around 10 Gauss. So it should be very easy to experiment and verify to detect this quantum sphere effect. We also, in our paper, we also develop other type of quantum spheres, like break parity, breaking other symmetries, and there's a systematic way to deal with that. So interested audience can go to check our papers. Now I come to the conclusion. So the take-home message is quantum fluctuations make symmetry breaking information of a material leak outside. So the first part is the symmetry breaking plus quantum fluctuations leads to anomalous force. And the second part is the symmetry breaking can leak outside of the materials due to quantum fluctuations. So thank you very much for listening.